what we're being asked to do here is to set up an integral that finds the volume that's bounded by z equals 1 minus x, z1 minus y in the first octant. I'm going to make two sketches, a bad one and a good one. We're sitting in the first octant, so I'm going to draw that first. Now z equals 1 minus x is a plane, but it's actually the way we draw this plane is like a cylinder because it doesn't have nice intercepts. So z equals 1 minus x looks like a line that looks like that, but it goes forever this way. So I go like this, I go like this, I go like this, I go like this, and that's just this plane up here like this. Z equals 1 minus y is very similar. If I draw the line z equals 1 minus y, it seems to look like that, but x can be anything. So this one comes back this way, like this, and goes over like this. Let's see here, and it comes down like this, and goes over like this. And what happens is the brown plane hits the blue plane, right? And you're going to get this intersection of a line where they hit. Now you can see that the region we're interested in here is going to be this little piece in here, which we'll draw in just a second, right? I need this, I need this, I need this, and this, and this. I actually had you draw this in the first chapter, but this is exactly why. These kinds of problems show up in statistics, so we want to be able to do them. Meanwhile, I'm going to draw a better picture, one that's not so full of extra lines that I don't care about. So here we go, drawing a nice picture, right? We know that this one went like this and came this way. We know that this one went like this and came this way, and then where they hit each other looked like that. Now, I do want to do a triple integral here, and so I want to start drawing lines. The one thing you don't want to do here is draw lines parallel to the z-axis, because this is a tent that has two tops. If you're sitting over on this half of this rectangle, the top is this part of the plane. If you're sitting over here on this part of the rectangle, the top is now different. We don't want to have to do two different integrals, and I'm not gonna. What I would like to do is either draw a line parallel to the x-axis or parallel to the y-axis. I'm going to draw parallel to the y-axis because I think it's just easier to draw. Here we go. I draw a line parallel to the y-axis. It enters at the xz plane, and now it stays inside, stays inside, stays inside, and then it leaves on this slanty plane over here. Now I drew a line parallel to the y-axis, right? So we're doing dy first. And so I need to know what y is as it enters. Well, that's just the xz plane. The equation of the xz plane is y equals 0. It's leaving right here at the plane z equals 1 minus y, but I want to know what y is, and that's is y equals 1 minus z. So the limits of integration are then 0, because that's the y coordinate of when the chop hits the region, and y equals 1 minus z, which is the y coordinate as that chop leaves the region. I now need to smush. So we're smushing over here. What are we smushing to? Well, y is now gone. The only thing that can be left is x and z. Looks like that. Let's see, x and z, and that just looks like this line. In fact, that's the line z equals 1 minus x. And I have just enough room to write this down here. Now what I want to do is start drawing lines, either parallel to the z-axis or parallel to the x-axis. I really don't care. Let's just do x-axis and feel a little weird about it. Yes. I need to know what the x-coordinate is as that line enters the region. I need to know what that x-coordinate is as that line leaves the region. This is x equals 0 over here. This is the x-coordinate as it leaves the line. If z equals 1 minus x, then x is equal to 1 minus z. To solve for x, so I'm going to write it in a little x equals 1 minus z over here. And now we're doing a limit of integration for x, and we can see that the x-coordinate when the chop enters the region is 0. The x-coordinate when the chop leaves the region is 1 minus z. Like that. And now the last one is always constant. I can either smush again, or I can just say what was the location of the chops, but you can see that the location of the chops just runs from 0 to 1, so there's no need for actually further smushing. And that is a triple integral that gives the volume, and you can see that's actually quite an easy integral to do.